Hello, friends. Today we will discuss about three-phase solid-state DC drive. As I mentioned in the very initial class when we started with the DC drive, in the case of three-phase DC drive, there are two categories, two types. One is fully controlled, another is half controlled. We will take up now fully controlled bridge configuration, and we will try to understand this considering a separately excited DC motor, assuming that the DC motor armature inductance is very large. So the configuration that we are now taking up is three-phase fully controlled bridge solid state DC drive for a separately excited DC motor with large armature inductance. Once when I make this clear, you are already having the idea about the schematic, how the schematic looks like, the circuit looks like. The circuit is like this. Yeah. Can you see that? Now look here. We have three-phase AC. Three-phase AC with the supply voltage of the format, it is sinusoidal voltage. VL, the instantaneous line voltage, is equal to maximum line voltage VML into sin omega t. If the line RMS value is VL, then it is root 2 VL sin omega t. Next, this part is the bridge part. It is three-phase fully controlled bridge. That means all the 6 devices here are the control switches. We have considered the SCRs as our control switches. So there are 6 SCRs T1 to T6. Look at the way they are named: T1, T3, T5 upper, T2, T4, T6 lower. About the working of this, we have already discussed in power electronics, hence I will not go into too many details. It's a bridge rectifier. It's a fully controlled bridge rectifier. Here it consists of 6 SCRs. Now, since it is a rectifier, input is AC, output will be DC. That average output voltage is fed to the armature of the separately excited DC motor. So this DC motor armature is between A1 and A2, and armature has armature winding resistance RA. Assuming back EMF as EB, then the applied voltage VA will set this armature into rotation provided the field is excited. So the field excitation is shown here. It is separate. That's why the name, it is separately excited DC motor. Now we will look at the working of this. At the very outset, the working will make the first thing in this bridge, two SCRs conduct, one from upper and other from lower bank. This we know already. Let us register that in our mind. Condition. With the condition, what is this condition? For this not to be from the same arm. This is an important thing. What does that mean? If T1 is conducting, along with T1 it will be either T6 or T2. It cannot be T4. if T5 is conducting along with T5, it will be either T4 or T6, not T2. That's what we mean. Okay, that's one thing. Second, coming to the working, the second point is uh, SCR's pair, SCR pair. Two SCRs always conduct. Na? Which SCR pair conducts? Which SCR pair comes into conduction? SCR pair to come into conduction. If it has to come into conduction, what is it to be? It should be more forward biased, and then it should be more forward bias, and then it should be triggered. There are two requirements: that pair which is more forward biased and that pair which is having the triggering. These two conditions met, that pair comes into conduction. Is it okay? Now, to decide which pair is more forward biased, we go to the waveforms as we did when we discussed in power electronics. Look at this. This is the three-phase waveform. RY, YB, BR, and 180 degree opposite. VBY, VRB, VBR. All these are the voltages, line voltages, and it is actually a three-phase waveform with their counterparts, making it a six-phase waveform, and each one of them are displaced by 60 degrees. You have VRY, after that RB, after that YB, after that YR, after that BR, after that BY. Like that, it will be happening in a sequential fashion. Now, RY is the voltage, and that RY, this is RY, this is RY, this is B. This RY concerns to 1 and 6, T1 and T6. So I can trigger T1 and T6, and here I am triggering at this point at alpha is equal to what I am calling a 0. And when T1 and T6 start conducting, the RY voltage will appear across the output. Next, at this point, I trigger T1 and T2. T1 is already conducting, I will maintain the triggering. Now instead of T6, I will start T2. T1 and T2 pair will conduct. Since T1 and T2 pair corresponds to RB voltage, and you can see here, this is RB, and from this point onwards, RB is more positive than RY. Even if I have triggering to T6 intact, T1 T6 pair, T1 T2 pair in between, it is T1 T2 pair which is corresponding to RB is more positive, hence T1 T2 will start conducting, T6 automatically commutates. Hope I have made that point clear. Similarly, the next pairs T3 T2, T3 T4 will come into conduction, and we get the output voltage like this. This is the output voltage which is DC. So output voltage is DC. Output voltage, because there is no negative part here as such, it is DC voltage. And I made a mention, this point corresponds to alpha is equal to 0. Why? Because even if we try to trigger the devices earlier than this, it will not be possible, because the earlier voltage will be more positive, making the corresponding pair more positive, thereby avoiding this pair coming into connection. And that's why we will make a mention here, minimum firing angle is 60 degree. That is why that is taken as alpha is equal to 0. This is corresponding to 60 degree na. This is 60 degree na. That point I am taking as alpha is equal to 0. Good. Now for this alpha is equal to 0, output voltage is like this. In a period, in a duration of 360 degrees, in a duration of 360 degrees, as you can make out 1, 2, 3, 4, 5, 6, there are 6 pulses. So there is a output, DC output voltage, 6 pulses. Output pulses are how many? 6 pulses. Because the number of pulses is more as compared to single phase, obviously the output voltage is smoother. What does that mean? It means the ripple content is, ripple factor is less. This means a ripple is less. That means ripple is less. Hope you are catching that. Good. And now here this is the voltage, and below that only I have shown the current waveform. Can you see that current waveform? Good. Output current I have taken it as IA, and this I have shown it to be remaining constant. Why? What is the defense for me doing that? The defense for me doing that is this. I have assumed armature inductance to be very high. So because armature inductance is large, armature current can be assumed to be constant and continuous. Constant and continuous. And this mode of operation is called continuous mode of operation. Continuous mode of operation. So what we got now? We got the armature current which is remaining constant almost, and we have got the output voltage which is DC pulsating. There are ripples, but the ripple factor is less compared to a single phase case. It is smooth, ripple factor is less. Okay, good. So now by changing alpha, if I change alpha, then it will change the average output voltage. What is that average output voltage? What voltage I get here? What is the expression for this? The average output voltage expression is VA equal to 3 VML divided by pi cos alpha. Obviously, when I change alpha, VA also will change. And how the waveforms will change here? If I make alpha more, this pulse will start from this point, will continue up to this, start from this point, will come up to this. So you can see that yourself. If I change alpha, the waveform also will change, but the current in the armature will remain constant. Magnitude of the output voltage will change, and that expression VA 3 VML by pi cos alpha tells that when alpha changes, VA also changes. Now, interestingly, when alpha becomes yeah 90 degrees, what will be the value of VA? 0. So when I have this alpha 90, then we will have this waveform extending beyond 0. That's why in the output there will be positive as well as negative part. The average output will be due to both positive and negative. If both of them are equal, then the average output voltage will be 0. That's what happens here. So you can see alpha more than 90 degrees, VA will be negative. Alpha less than 90 degrees, VA will be positive. Alpha is equal to 90 degrees, VA will be 0. So that change in VA I can represent in a very simple fashion like this. This is alpha, this is 0, 90, this is 3 VML by pi, this is 3 VML by pi. Good. So that VA, average output voltage, can be negative, can be positive, it can be 0. Okay. So accordingly, when I have the voltage across the armature changing, what does it mean? It means the speed of the armature also changes. The speed of the armature also changes. That is why by changing alpha, thereby changing VA, I can change the speed. I can change the speed. That is how this can become a control approach for a DC motor. So what I will do now, I will show here. See, I will show here. I will take the input. I will take the input from the armature, and that input, let us say, is N. Using that, I will generate the firing pulses. I will call this as controller. I will call this as controller, and from the controller I will get firing pulses. Firing pulses. These firing pulses will be T1 to T6, the SCRs. So what I will do now, I will measure the speed of the armature, the motor, and I will get a signal corresponding to that. It can be a tachometer, a tacho generator, and that speed signal I will use in the controller, which is typically a processor. I will take the decision whether the speed present now is as per my requirement, more or less. Accordingly, I will take the decision as to what is to be the firing pulse. That firing pulses I will give to the SCRs, so that the output voltage will accordingly change, bringing the speed of the motor as per our requirement. Okay, so this this actually makes the control possible for the motor. This makes speed control. This makes speed control. It makes the speed control. Okay, so here we made a mention that the output voltage can be positive or negative. So when VA is positive, the machine will be acting as motor. It is forward motoring. Machine will be operating as motor in the forward direction. If the voltage is negative, then the machine will act as a brake when running in the forward direction. So we can call it as forward braking. We can call it as forward braking. So these two can be shown in the form of the quadrant of operations, wherein this is T, this is omega, this is forward motoring, this is forward braking. It has two quadrant operations, which means two quadrant operation. Two quadrant operation. What are the two quadrants? the forward motoring and forward braking, forward motoring and forward braking, two quadrant operation. How that became possible? Because the voltage can be positive or negative depending on the value of firing angle alpha. Depending on the firing angle alpha. Good. So you can make it operate in two modes. You can make it operate in two modes. Next, one more thing that we will see here, that is output voltage waveform. Output voltage waveform, that is little interesting. See here, the output voltage waveform is this VRY, VRY, VRB. This is a very simple configuration situation because the conduction is continuous. It's a continuous case. If the conduction is discontinuous, something interesting will be there. This waveform will be different. This I showed you in the case of single phase case, na? The same thing I will show here, little simple form. This is for continuous case, we have seen there already. For discontinuous conduction mode, how it will be? Only one pulse I will show. Please observe this carefully. We have one pulse. We have one pulse started, and this ends. The next pulse has not yet started here. This starts somewhere here, let us say. So the pulse which has started, I have started the devices here by giving firing. The output I have got like this. It will reach 0, and it's a discontinuous case. The extension of conduction may be the slight, because discontinuous conduction happens only when the inductance is less. Hence the extension of conduction will be less. After that it will come to stop. Conduction stops, but the next pulse is starting little away after a gap. And then what will happen in between? Here this is alpha, this point is beta. This is the next instant of triggering. From here to here, will there be voltage across the armature? Yeah, there will be voltage. And what will be that? That voltage will be the back EMF. That voltage will be the back EMF. With this, the output voltage waveform will be like this, roughly. Can you see this? So in the continuous case, back EMF was not visible because the supply voltage itself was present all through. But in the case of discontinuous case, you will have the back EMF also coming into picture, because there is a patch period of discontinuity when the supply totally gets cut off. When this happens, then in the corresponding interval you have this. This is output voltage, whereas output current, how the output current will look like? See, from this point to this point, there is a, yeah, from this point to this point you have the back EMF appearing across the armature, and from this point to this point the supply voltage is there. So from this to this you will have the bridge devices conducting, whereas from this to this you will have you will have no conduction, there will be discontinuity. And this discontinuity means there is no current here as such, no current here as such. So you have one pair conducting, no conduction, the other pair conducting, like this you will have the current waveform. So the current waveform will be something like this. Current waveform will be something like this. From here to here there will be no current, there will be no current. Okay, now so the situation can be slightly extended as much as the discussion is concerned. Now what I would like to convey to you is, this is a configuration with two quadrant operation, if I would like to convert this, if I would like to convert this as single quadrant configuration, what I can do, what I should do, I can convert this by having a parallel freewheeling diode, by connecting a freewheeling diode across armature. Yeah, the configuration, the scheme becomes half control, nothing but single quadrant operation, what do we do then in this circuit? Here we connect a freewheeling diode. When that freewheeling diode is connected, then the output going negative is avoided, the output going negative, this is avoided. And this interval, the freewheeling diode starts conducting. And the freewheeling diode present there will also allow the armature to dissipate its stored energy, and as a result the current can continue in this period. If the stored energy is more, the current can as well become continuous. Only thing is, this period the freewheeling diode conducts, this period the bridge devices will conduct. Okay, so we have, by connecting a freewheeling diode, the bridge becomes, the configuration becomes single quadrant configuration. Good. So in this whole thing, what we observe is, slightly the control is complicated, because you have 6 devices, all the 6 devices are to be managed. So keeping that in mind, we look at the applications. So the applications, three-phase DC drives are used in contrast to single-phase DC drives for large motors, employed for large motors, large DC motors, as compared to single phase, and the basic advantage of this is, the whole thing becomes compact, that's on one side. The second biggest advantage is the ripple factor becomes less, basic ripple factor becomes less, and as a result the filter that we need to use, if at all we have to use a filter, that filter will become more simple and then more compact, employed for large DC motors. And thus we should make a mention, three-phase drive versus single phase drive. three phase drive versus single phase drive. So please try to make a comparison between the two in the light of the discussion that we have already made. Hmm. And one more thing that you have to focus on is, I told by connecting a freewheeling railroad across the armature, it can become a single quadrant converter. That is a full bridge getting converted into single quadrant converter. Now, instead of that, if I want to have basically a single quadrant converter, then what I will do, I will not take full bridge at all. I will not take full bridge at all. I will take half bridge itself. Okay. So here I will make a mention. The half bridge is with 3 SCRs and 3 diodes. This I should keep in mind. So if my intention is requirement is single quadrant operation only, then I will go for half bridge with 3 SCRs and 3 diodes. That will make the cost of the whole bridge less. The control also simple because only 3 devices are now controlled in nature. Is it okay? So we shall stop there. Next class we will continue.